Now, next next theorem is, let N be a norm linear space and suppose two norms, norm 1 and norm 2, are defined on the N. Then these norms are equivalent. So these norms are equivalent if and only if it satisfies this condition, right? So these norms are equivalent if it satisfies this condition. So remember, when the norms are equivalent, if they introduced same topology on N, it means if they introduce the same topology on N, it means the open set with this norm is also open set with that norm, right? So it means they induce the same topology on the norm linear space N. So what we will do, so you will understand this theorem by doing a proof. So we have one norm linear space N and two norm. One is norm 1 and second is norm 2. So this is N is normed linear space. N is normed linear space, right? Now there are two norm 1 and norm 2. So if with this N I take norm 1, so this norm space is denoted by N1, right? So N with norm 1 is denoted by N1. It means it has all the vector of N, but with the norm 1. So that is that vector operated with the norm 1. Similarly, in the second norm, we take this again N with the norm 2. Again this N is this N, the vector of these N, this operated with the norm 2. So these are N1 and N2, two norm linear space. They have same element, they have same vector, but with different norm. Clear? So that is my first purpose to construct N1 and N2. If I construct N1 and N2, so these are the different norm linear space. Now I define a identity transformation. So this is a N1 and this is a N2. This is a N2 and T is mapping from N to N1, and this mapping is defined by Tx equal to x. So this is a for every x belongs to N1, but we can also write it as x belongs to N because vector are from N. So this is x belongs to N. Now this T is identity operator. So it is a linear transformation, number 1, because it is an identity operator. Identity operator are linear transformation. Number 2, it is a bounded. So we can also say that it is a bounded linear transformation, or we can also say that it is a bounded operator. So I define this T which is from N1 to N2, and this is defined by T of x equal to x. So this is a bounded operator, the bounded linear transformation whose domain is N1 and whose range is N2. So remember, whose domain is N1 and range is N2. Similarly, its inverse map, which is from N2 to N1. So this is again bounded linear transformation, right? This is again bounded linear transformation, and we can transformation, and we can define the T inverse x from this. So what is that? Again, T inverse x is again identity operator for every x belongs to n. Now this T inverse, whose domain is n2 and range is n1. So remember this both T and T inverse are bounded linear transformation, and we can also say that it is a continuous linear transformation. So what we get if it is a n1, this is a n2, right? So T is mapping from n1 to n2. Similarly, T inverse, which is a mapping from n2 to n1, right? Also, we know that T of x, which is equal to x, and similarly T inverse x, which is equal to x for every x belongs to n, right? The only difference is norm. So here it is x, that again goes to x. Here it is x, that again goes to x, right? So this is a simple identity operator. Now from this, if T is bounded operator from n to n, so by definition of bounded operator, it implies there exists a positive constant C such that norm of Tx, which is less than equal to C into norm of x, right? For every x belongs to n. It implies what is norm of Tx? That is x. Now here just see that this x belongs to n1. So here it is a norm 1, and here T of x belongs to n2. Here it is a norm 2. So difference is only with the norm. So it implies norm of x2, which is less than equal to C norm of x1. Remember that, right? So this is a if and only part, because T is a bounded operator. So that we did by using this result, right? Now from this, again on the same parallel line, so there exists some positive constant, that may be C, that may be D, we can use any one. So here I use B because of the given part in the question. Here it is a B. So again, by using T inverse is a bounded, T inverse is a continuous. So again we can use the same concept. So there exists a positive constant, C such that norm of T inverse x less than equal to C norm of x, right? Now again see it. Now this x belongs to n2. So it means this x has a norm 2. T inverse x, its image is in n1. So its norm is norm 1. So if and only if again this is norm of x1 less than equal to C time norm of x2, right? If and only if this values, this is a 1 by C, which is a norm of x1 less than equal to norm of x2, right? Now by using the result C, what is C? C is a constant. If C is a constant, so 1 by C is also constant. So this can be written as A into norm of x1 less than equal to norm of x2, right? So this values. Now these two result, when we combine these two result, this result and this result, then we get a norm of x1 less than equal to norm of x2 less than equal to b norm of x1 for every x belongs to n. So that we get because T and T inverse are the bounded linear transformation. So that's why we get this result. Now again, when we used the continuity of linear transformation, then what we get, we know that the inverse image of continuous function is the inverse image of the continuous inverse image of open set is again open, right? So here this is T map, this is from n1 to n2, so this is n1 to n2, or here it is a T inverse, so this is from n2 to n1, so remember that n2 to n1, clear? So this values. Now since T is continuous, so it means if we take here open set G, then it inverse image T inverse G is open in n1, right? Similarly, if we take some G dash, the G open set in n1, its inverse image is T inverse G is open in n2, clear? So what we get, because T and T inverse is identity operator, so basically it is a G, and basically again it is G. So its open set in n1 is open set in n2, clear? Similarly, open set in n2 is open set in n1. So what we get? We get open set in n1 and n are same. So what we get? We get open sets in n1 and n2 are same. Why this is possible? Because these are continuous linear transformation. If they are same, then what we get? They introduce the same topology on n. If and only if norm 1 and norm 2, right? They introduce same topology on n. Why? Because open set with the norm 1 and open set with the norm 2 are same, clear? So it means they induce same topology on n. So this induce same topology on n. So don't confuse yourself with the word topology. Simple remember, open set with the norm 1 and open set with the norm 2, they are the same. If they are the same, they induce same topology on n. So it means these are definition of equivalent norm. So norm 1, if they induce same topology, then these norm are equivalent, clear? So norm 1 and norm 2 are equivalent. So if norm 1 and norm 2 are equivalent, they induce same topology on n, number 1, and they satisfy this condition, A into norm of x into norm of x1 less than equal to norm of x2 less than equal to b norm of x1, clear? So here what is the meaning of the equivalent norm? The meaning of the equivalent norm, there are two meaning of the equivalent norm. So one meaning is there exist two constant A and B which satisfy this condition, A norm of x1 less than equal to norm of x2 less than equal to b norm of x1. That is a one meaning. And second meaning is norm 1 and norm 2. Norm 1 and norm 2, they induce same topology on n, on non-linear space n, right? So by mathematical, this can be written as norm 1 and norm 2 are equivalent, right? So there are two definitions. One definition is they induce the same topology on n, and second definition is a norm of x less than equal to norm of x2 less than equal to b times norm of x1 for every x belongs to n, right? So this is a second definition and this is a result. Now, in addition to this, we define a very important norm which is called a zeroth norm. And zeroth norm is defined only for finite dimensional vector space or finite dimensional vector space, or finite dimensional non-linear space. So this is called a new term, zeroth norm. Now suppose n is norm-linear space. N is normed linear space. N is norm-linear space and it is finite dimensional. So dimension of n is small n, right? Dimension is small n. If dimension is small n, then it means it has a basis. Suppose E1, E2 and En, right? So this is a basis of non-linear space n. If this is a basis, so we can find for every x belongs to n, there exists a scalars alpha 1, alpha 2, alpha n such that this x is equal to alpha 1 E1, alpha 2 E2 plus alpha n En, and this expression is unique. Also in summation form, this can be written as alpha I Ei, and I is running from 1 to n. This is a summation form. Clear? So this expression is unique because it is a basis. If it is a basis, so this expression is unique. If this expression is unique, what is the zeroth norm? So zeroth norm is norm x vector denoted by 0 at the lower part of norm. So this is a maximum values of absolute value of alpha I, right? So this is a maximum value of alpha I, and this is called a zeroth norm. So this is the definition of zeroth norm. So remember this definition. So this is very important. So we will use in the many examples, many results that we will do now. Now, after that, if we define this zeroth norm, so after that there is very important result and very tough result expected for examination, as well as it is for application. So its application is very important and also it is expected for examination. So what is that result? So that result is all finite dimensional space, on a finite dimensional space, all norms are equivalent. So this is very important result. So what is the statement of result? So statement is, in this theorem, on finite dimensional norm space, on finite dimensional space, all norms are equivalent on finite dimensional space, all norms are equivalent. So this is very important result. So we will use it in a many application. So if space is finite dimensional, then the all norms are equivalent. So in that case, they induce the same topology. But in the case of infinite dimensional, so it is not necessary the all norms are equivalent. Now we take, let I take n is a nonlinear space, finite dimensional nonlinear space with the norm, let n is finite dimensional normed linear space, normed space with the norm this, right, with the norm this. So this is a very tough theorem and lengthy theorem. So have patience to understand it and to do it, and you will definitely understand if you see this video properly. Now, if this n is finite dimensional vector space, norm space, with the norm is norm this, then it has some dimension. Suppose that dimension is dimension of n is equal to t. Suppose I can also choose n, but there are in the sequence I will choose n. So I take this is t, you can also take it is s, p and any other number. So we can also use the p, also we can use the p. Suppose this is a dimension of n is p. If a dimension of n is p, then this E1, E2 and so on up to EP. So what is this? It is a basis of norm linear space n, right? If it is basis of norm linear space n, then for any x belongs to n, this can be written as x which is equal to summation of alpha I, ei, I is running from 1 to p, and this expression is unique. Yeah, we can express uniquely expressible as a linear combination of E1, E2, E3 and E1, and also where alpha 1, alpha 2, alpha p, these are scalars. So these are scalar. Write it as equation number 1. If we can write it as x as a linear combination of these values, and it means what is the zeroth norm that we already defined. So zeroth norm of x is maximum value of alpha I, right? So that is a maximum value of alpha I. So that is a zeroth norm. Now on n we know that let this is a norm on n, that is given part, right? So this is a 0th norm. So there are 2 norm on n. For every x belongs to n, we can write it as norm of x, substitute the value of x, alpha I ei, I is running from 1 to p, and this is a norm. Clear? So this is a norm. Now this, by using triangle inequality, so this is less than equal to summation of I 1 to p norm of alpha I ei. So this can be written as summation of I 1 to p absolute value of alpha I into norm of ei. Clear? Now each alpha I is less than equal to its maximum values. Clear? So this can be written as less than equal to maximum value of alpha I. So I take it outside from summation, and summation of norm of ei, and I is running from 1 to p. Clear? So these values. If I take this term as constant m, and what is this? This is a norm of 0th norm. So this will be less than equal to capital M norm x 0. So this is equation number 2, right? So we did first part. What is the first part? So first part is norm of x less than equal to capital M time norm of x 0. So I did first part, which is a norm of x less than equal to m time norm of x 0 for every x belongs to n. So this is equation number 2. So this is the first part. Now second part. Second part, our claim norm of x should be greater than small m constant norm x 0. So that is our second part. So first part is less than equal to, and second part is greater than equal to these values. Right? Now we shall prove it with the help of mathematical induction. So what is my aim? My aim is small m x 0 less than equal to norm of x. That is my aim. So we shall prove it with the help of induction, mathematical induction. So first step is result should be true for p equal to 1, and then assume the result is true for p minus 1, and then prove for p vectors. So first we suppose p is equal to 1, right? If p is equal to 1, then x vector is alpha 1 into e1, right? Clear? So very simple. Then it implies norm of x, which is the norm of alpha 1 e1, and which is absolute value of alpha 1 into norm of e1, and this value is maximum value of alpha 1, because it is a single value, so its maximum is itself, into norm of E1, and this is norm of x0 into m, where small m is equal to norm of E1, right? So we prove first result. The result is true for n equal to 1. So here equality is applicable, not less than. Here equality is applicable, so our result is true. Now let p is greater than 1. Now for the, and assume result is true for m minus p minus 1 vectors, right? And my purpose is to prove that the result is true for p vector. So I assume this is a true for p minus 1 vector. I take a new subspace M dash. This M dash is subspace spanned by, this is spanned by p minus 1 vector, E1, E2 and EP minus 1, because our result is true for p minus 1 term. So this is a subspace of n and spanned by p minus 1 vectors. Clear? And our result is true for this m dash. And by equation number 1, that part is also true. So for this, it is a true for p minus 1 vector. Clear? Now from this we know that by induction for p minus 1 vector, m into norm x0, so this is less than equal to norm of x for every x belongs to m dash, because our result is true for p minus 1 vector, this. And the first part is true for every p vectors, so that is also true for p minus 1 vector. What is that result? That result is norm of x less than equal to m into norm of x0. So it is also true for x belongs to m dash. Clear? So one is by using the induction, and second is we already proved the first part for m, so that it means if it proved for the m, then also it is proved for the m dash. Clear? Now combining these result, so what we get? We get m norm x0 less than equal to norm x less than equal to capital N norm x0. This is for every x belongs to m dash, right? So this is m dash. Write it as equation number 3. Clear? But my purpose is to prove in the case of m. So I prove in the case of m dash. So my purpose is to prove in the case of m. So how we will prove that? Now from this, these two norms are equivalent on m dash. It implies norm simple is equivalent to norm 0 on m dash. So remember this result. We will use it, remember. right? So we will use it. Now these are equivalent. Suppose let this Yn be a Cauchy sequence in M dash with norm this, right? Because these norms are equivalent, so it means this is again Cauchy sequence in M dash with norm 0, right? So this is a Cauchy sequence with the 0th norm because they are equivalent. If equivalent, then it implies by definition of Cauchy sequence Yn minus Ym 0th norm approaches to 0 as Mn approaches to infinity, right? So this is a definition of 0th norm. Now we will find the value of Ym minus Yn. We know that this Yn is a sequence. This can be written as, this Yn is a some sequence. This can be written as alpha 1 E1, alpha 2 E2 and so on. So using that result, so just here this Yn, which is equal to alpha 1, here I am taking n, E1 plus so on up to alpha p minus 1, alpha p n, because it is Cauchy sequence in M dash. So it is a combination of p minus 1 vector. So EP minus 1. Similarly, Ym alpha 1 m, E1 so on, alpha p minus 1 m, EP minus 1 vector, and Yn minus Ym. This will be summation of alpha k n minus alpha k m e I e k. K is running from 1 to p minus 1, right? So what is its 0th norm? 0th norm Yn minus Ym, which is a maximum value of alpha k n minus alpha k m, these values for every k, right? As this 0th norm is approaches to 0, Mn approaches to infinity. So this approaches to 0 as Mn approaches to infinity, right? It means this sequence alpha k n minus alpha k m again approaches to 0. So it implies alpha k n minus alpha k m, this sequence approaches to 0 as Mn approaches to infinity, right? It implies this sequence alpha k n, which is Cauchy sequence in R or C. Since R and C are complete, so it means there exists scalar alpha k belongs to R or C such that it is a convergent mean alpha k n, which is equal to alpha k when limit n approaches to infinity, right? So this is by using the definition of completeness. So it convergent to this values. If it converges to this values, also if I take this y, which is a linear combination of this alpha k, e k, where k is running from 1 to p minus 1, right? So clearly yn, clearly this yn approaches to y as n approaches to infinity, right? With respect to zeroth norm, with respect to norm zeroth, right? Now, since both the norm are equivalent, so it is also convergent in the second norm. If it is convergent in second norm, then it implies this yn convergent to y as n approaches to infinity with respect to norm, which is this norm, because both are equivalent. So this is a yn, this is a convergent. It means the space m dash with this norm is complete. Why complete? Because every Cauchy sequence with the norm, this norm is convergent. Clear? So this is our first part. This space m dash, which is a subspace of p minus 1 vector, so this is a complete. Now, but our result is to prove m vector for m vectors. Now I consider the pth vector, pth basis vector. So that is left, that is EP, right? Now define a set which is EP plus m dash. What is m dash? M dash is spanned by p minus 1 vector. One vector was left, so that we taken as addition. Now this is a set of EP plus Z, and this Z belongs to m dash, right? So remember this Z belongs to m dash. Now what is m dash? M dash is complete, and complete metric space are closed, so m dash is closed. So remember, this m dash is complete, right? And complete space are closed, so this m dash is closed. Clear? So m dash is closed. So remember. Second, this is isometric to m dash. So En is isometric to m dash with the transformation, with mapping. What is the member of m dash? Z, with mapping Z from EP plus Z, right? So this is there is no need to prove it. So this is a isometric to M dash. Now if M dash is closed, then its isometric subspace is also closed. Then it implies EP plus M dash is closed, right? If it is closed, then EP plus M dash complement is open set. This is a open set. So remember that this is a open set. So it is our first part. Second part is 0 belongs to this set. 0 belongs to this set means 0 does not belongs to EP minus M dash. If 0 belongs to its complement, then it means 0 does not belongs to EP plus this. Now suppose 0 belongs to EP plus M dash, then it means 0 is equal to EP plus alpha 1 E1 plus alpha 2 E2 plus alpha P minus 1 into EP minus 1, right? Clear? So what it indicate? It indicate these vectors are linear dependent, but because of bases E1, E2 and En are EP are linear independent, but because here it is a non-zero, so it shows it is a linear dependent. So which is absurd, which is not possible, which is absurd. If it is absurd, then it means 0 does not belongs to EP plus M dash. It means 0 belongs to its complement M dash and its complement. Also this is a open set. Also it is a open set. Now using the definition of open set, if we take any point from that set, then the neighborhood around that set, neighborhood, open ball, just sphere, is contained in that set. It implies, so this is a open ball of 0, right? Because 0 is a member of this, and radius is suppose Cn, which is contained in EP plus M dash complement. So what is this set? This set is all x such that norm of x less than equal to Cn. So this implies is part of EP plus M dash complement, right? Then it means this set is a part of EP plus M dash C. Then it means it implies this set X such that norm of X greater than Cn is a part of EP plus M dash, right? So EP minus M dash. Clear? So this satisfies this condition on this satisfy this condition for this values. Yeah, here I take a mistake, so just first now this set is subset of this, then its complement is in reverse part. So EP, so its complement EP plus M dash, which is a part of set X such that norm of X greater than Cn. Clear? So this is this values. Now take some member from this. What is that member? That member is alpha 1 E1, linear combination of this. That member is alpha 1 E1, alpha 2 E2 plus so on, alpha P minus 1 EP plus EP, right? So this is a X member which belongs to EP plus M dash, right? So it satisfies this condition. If it satisfies this condition, then it means norm of X, which is alpha 1 E1 plus so on, alpha P minus 1 EP minus 1 plus EP. So this is a greater than norm of Cn, which is absolute value of Cn. Then we can simply write it as Cn, right? So this can be this values. Now replace, because these are scalar, alpha I by alpha n. Clear? So just replace in this equation. If we replace in this equation and substitute that values, so what we get? We get norm of alpha 1, norm of, so we get norm of alpha 1 E1, alpha 2 E2 plus so on, alpha P EP. This is greater than absolute value of alpha P and Cp. So just correct in the previous part, that is not a alpha n, that is a alpha P. So here alpha P, here Cp. So correct it, because we are taking P vectors, right? So here it is a Cp. Now if we correct this as, so what we get? We get norm of alpha 1 E1 plus so on. So I get these values, norm of alpha 1 E1, these values, norm of plus alpha 2 E2 plus alpha P EP, and so on, these values greater than alpha P absolute value into Cp. So just substitute these values. Yeah. Now we are very near to our result. So here remember that norm. So this is greater than, right? Minimum of, so this we can do it for, similarly we can find Ci greater than 0. So here we did for Cp. So similarly we can find for Ci greater than 0. What is that? Norm alpha 1 E1 so on alpha P EP which is greater than absolute value of alpha I into Ci. So this is a positive, so Ci. Clear? Now this value is greater than, here I take maximum and here I take minima of Ci. So there is no difference in the equation. So here maximum and second is minimum. Why I am taking maximum and minimum? Because my purpose is to find the norm of 0. So this is a greater than norm x 0, right? So this can be written as minimum of Ci. So this is written as norm of M. So what is this? This is a norm of x. So this is greater than M into norm of x 0. So which proves the second part. So first part and second part. So combining these two results, what we get? We get small m norm of x less than equal to norm x, so it was 0th norm, less than equal to capital M norm of x 0 for every x belongs to, so that is a, for every x belongs to the entire space N. So this satisfies for p vectors. If it satisfies p vector, then it satisfies for n vectors for n space. Now it means these norm are norm, this is equivalent to this 0th norm. So this is very important result. So remember that result. In finite dimensional vector space, in finite dimensional norm space, normed space, all norms are equivalent. So this is very important result. All norms are equivalent. So remember that result. This is a tough theorem. So do it 3 to 4 times, then you will understand the entire theorems, right? So for finite dimensional norm space, all norms are equivalent. So this is also very important result for a university examination.